Okay, yeah, thanks for the introduction. And it's actually great to meet you like in online to actually tell you a story about our recent progress on discovering this fractional quantum Anomalous Hall effect in R stacked or rhombohedrally stacked twisted MoTe2 telluride system. So I'm Jiaqi, PhD student from Xiaodong Schu's group at the University of Washington. And there is a series of a report that we recently published by Eric about the quantum mechanism. Mechanism is a basis, but I won't talk a lot about it today, but it's also very interesting. And if, there's another paper after that, it's, I mean, almost the same time, it's about the optical signature of this fractional quantum Anomalous Hall effect, the states, basically. But finally, very recently, we reported the observation of this Hall effect, basically in transport measurement. So that's the definition of the Hall effect, Hall measurement. Okay, so first I would like to thank to my founding agencies that support this study, and my PI, Xiaodong Schu, who lead this study, and a very brilliant graduate student that collaborated with me, including Eric, Will, Hinjun, and Kai, who is a master student who provide very high quality flakes and help to fabricate the devices. And okay, let's get started. So let me get a short recap on quantum Hall effect. Maybe in this audience, I don't have to talk too much about the background, but what we actually see is that in a Hall bar device, basically here is a silicon MOSFET. When it's subject to high magnetic field, what you see is a very anti-intuitive phenomena that your Rx actually vanishing and XY forms some unusual plateau that is fraction of the universal constant H over E square. Okay, and this is very intuitive because it's a very good, it tells us that inside the system you have very good conducting channel, as well as the system is actually insulating, because if you calculate sigma x-axis, it's actually vanishing. So then the 1985 Nobel Prize is actually awarded to the discovery for this quantized Hall effect. Okay, so what we learn from this quantum Hall effect is actually physics in the Lambda levels, including there are lots of physics inside the Lambda level. I just name a few. Large degeneracy discovered by Landau. That's the initial study where we call it Lambda level. Then we know it has a quenched kinetic energy. It's also discussed by Hofstadter, how basically lattice effect can actually make it slightly disperse. Okay, Dirac fermion from lattice effect is protected by some topological number, and finally is the band topology of the base, the ground state wave function. As I show here, basically TKNN, Zolis, my advisor's collaborator, discovered a formula that only depends on the ground state wave function, these two form, a Barry curvature, and the integral and the summation below, like below the Fermi surface, they give you a topological number. And then Simon told us this is just a realization in condensate matter of the Chen invariant. Okay, but how we actually know that it's actually topology that works for this quantum Hall effect? We need some lattice effect that only involves topology rather than any other fancy property of Lambda level. Actually, that's exactly what Howden did. Howden construct a lattice model that actually have non-zero chain number, and it can gives you a quantized Hall effect. So this tells people that actually not only the band structure matter, the wave function and the ground state topological number also matter. And then if you project it to a torus, for example, in this case, you can see the edge state actually emerge on the end of the not torus, cylinder, on the end of two cylinder. Okay, so then it actually gives us a way to realize this quantized Hall effect without magnetic field in this lattice. But a more important thing that this Howden model tells us is that topology is actually the key for integer quantized Hall effect. Okay, so along this way, people can actually design new materials that actually realize this integer quantum Hall effect without magnetic field. That is called quantum Anomalous Hall effect. Okay, it's experimentally discovered by Cui Zhu, now a assistant professor in PSU, and also Qikun Xue in China. So what we actually see, the experimental hallmark of this quantized anomalous Hall effect is two things. One thing is that you see magnetism. Basically, the ferromagnetism is down to zero magnetic field. So if you swing magnetic field back and forth, you can see this hysteresis loop in your whole conductivity, and the jump of Rxx because of domain flipping around the so-called coincident field. Okay. Another thing is the hallmark of topology inside the system is actually the quantized Hall conductance. Okay, the Hall resistance actually quantized at h over a square associated with this vanishing longitudinal resistivity. Okay, so actually we can now achieve this quantized Hall effect even without lambda level. The question is now that the story is actually now beyond this integer quantum Hall effect, the so-called fractional quantum Hall effect. Fractional quantum Hall states is actually when you put even a higher magnetic field and with a higher device quality, basically a quenching of some specific disorder. Okay, so what you can actually see is now a kink on RxX and a plateau forming at 3 h over basically 3 h over e square. Okay, that means it's actually a fraction of the conductivity, the Hall conductivity. And what we now know is that actually the magnetic degeneracy actually is broken by interaction and open quasi-particle gap, and that's what discovered by Laughlin. Okay, so from this picture, we can actually now include more flavors from lambda level, basically large degeneracy, quenched kinetic energy that give rise to strong interaction, Coulomb interaction on the lambda level, and open a quasi-particle gap that give you this kind of phenomenon. But the organizing principle beyond this classical topology, this chain number of the integer quantum Hall effect is actually not realized back to 20 years ago. And now we know the key is actually interaction. So to search for fractional quantum anomalous Hall states, now we get a map. We want to learn from quantum anomalous Hall effect and learn how we got a fractional quantum Hall effect from integer quantum Hall effect. So what we know is we need strong correlation inside the system. We need magnetism. Basically, we need zero field, time Rosa symmetry broken states, and we need topology, topological number inside the system, basically Hall conductivity. Okay, so let's come to the today's talk. Actually, I will talk about rhombohedrally stacked twisted moly that tolerate. This is our experimental new platform. And our props, basically, we have different optical access, we have electrical access to it. Then we'll search for this fractional quantum anomalous Hall effect first. And then I will tell you that how we actually achieve this observation of a fractional quantum anomalous Hall effect in transport measurement. So that's the discovery. So let me give a short recap on the Moray quantum matter and what we achieved in the past like a few years. So what Moray is actually you have two pristine layer and we twisted with respect to each other with a marginally twisted angle, say a few degree. And now you can see new lattices actually form. There's a new ordered pattern that you can see from my screen. And what people found that we can achieve is that this rationally engineer band structure. Okay, so by controlling the twist angle, the layer, the electric field, etc., you have external knob that you can actually control the band structure and also the interaction of the system. And another thing you will notice is that because you increase the lattice spacing effectively, basically the long range interaction actually play a more important role because you now dilute the hoping. Okay, the wave function overlap between this. You can treat this high symmetry point as a diffusion atom or something. The wave function overlap between each other is decreased by increasing the lattice spacing, but the Coulomb interaction is still long range and pretty strong. So the Coulomb interaction start to play a very important role in that system. And all the people, another thing that people actually found is actually you can get this gate tunable topological flat band. Basically, you match something that we need for fractional quantum anomalous Hall effect. Okay, that's why we choose this system. So people actually found them. For example, signatures of strongly correlated states. An example is this beautiful superconductivity that mimics the phase diagram of Couperitz. Another discovery is this quantized anomalous Hall effect. It's an integer quantized anomalous Hall effect in some symmetry engineered twisted bilayer graphene system. Basically, you align it with the HBN, so you break certain spatial symmetry, and you can get this non-trivial topological states. Okay, so but there's a problem with this material. What's wrong with it is that those idea Moray superlattice is actually never there. Okay, so normally what you see is kind of a domain and a heterostring of these array structures, and how we can actually access this physics is very different from what we learned before. Okay, so let me show you two examples, array basically in real life. So what you actually see is a freshly clipped graphene surface, and it naturally formed this array. Okay, and if you take a scanning tunneling electron microscope to look at the tomography of this layer, you can see it's basically very disordered. Okay, you have domain here and there, and that actually forbids you how you can observe the system. And you would ask, how about artificially stack two layers rather than fractionally cleave those material? But that's what we actually do now. If we artificially stack two layers together and get this array pattern, it's more or less better than naturally cleaved one, but it's still very disordered, you can see. So the question is that with this disordered first generation sample, can we access some physics? So the question is actually, can we probe topological physics in nanoscale? Basically, can we probe the topology that happens on the boundary from the bulk measurement? Okay, but that's the question. Actually, the solution is rather simple, very direct, that the edge current can actually generate a bulk magnetization. And the bulk magnetization can be detected easily with the external local probe. Okay, so we use this very powerful Stratus formula. This is a thermodynamic argument that after you write down the grand potential, you can get the Maxwell relation. And by promoting it into a quasi-equilibrium, that you have a domain, you have like a gradient of chemical potential, you can prove a general formula that relates density of carrier, dispersion of the carrier density with respect to magnetic field to the edge hole conductivity with it. It's pretty natural. If you look at this picture, basically the changing of magnetization is related to the changing of the particle number, and then you can relate it this with Maxwell equation, the electromagnetic Maxwell equation. Okay, so that's the Stratus formula. It's actually tell us that the topological number is actually related to the dispersion of particle number with respect to magnetic field. And how people can detect topology with it. Let me show you another two examples that is early started to discover those non-zero field fractional chain insulator in graphene array. They are basically a lattice version of fractional quantum Hall effect, but they are not zero field. Basically, they still need high magnetic field to achieve, for example, topology or flatten the quantum geometry that we know from the second work. The first work is bilayer graphene aligned with HBN, and with 25 Tesla magnetic field, you actually thread like a half of the flux quanta inside the system, and forming those Hofstadter band with downstream topology. And together with this array, you got a flat band, flat chain band, and the flat chain band actually give you this slope. If you compare this slope and use this formula to calculate the chain number, it can tells you different information, a different property, topological property of those states. Okay, and you can see those fractional chain insulator, or normal fractional quantum Hall states, starting from zero charge neutral point. Another is in twisted bilayer graphene. That you can also see this linear dispersion of the carrier density with respect to with respect to magnetic field, and the slope of this density actually also tell you a topological number. And in this case, you actually need 5 Tesla to get the slope to start to shift. Okay, so because in low field the band geometry is not an ideal. You need to apply a certain magnetic field to actually reach this fractional chain insulator. But the fractional quantum anomalous Hall effect in zero magnetic field still remain quite elusive to us. So now I will show you that a rhombohedrally stacked twisted monitor toroid is actually an almost ideal candidate for those fractional quantum anomalous Hall effect. It has a honeycomb structure, and it mimics a Haldane model a lot. It's actually because the spin and a valley degree of freedom is actually 2 copies of this Haldane model. It's actually a K-Merlin model. And with the layer orbital coupling, you have actually got the access that you can use electric field to polarize the lattice to create a chemical potential difference between this MX set and XM set. Okay, so the Hamiltonian is basically the K-Merlin type Hamiltonian together with the interaction. So for short range or on-site interaction, you got this Hubbard model. And in this case, the MX and XM site has a strong like a wave function overlap. So you got this Holmes coupling or exchange coupling that gives you ferromagnetism when you integer field the system. And you also have long-range detection. Okay, so now we got the system. What's actually the ideal prop? So actually, we now in our lab we develop those like kind of optical local prop of gap states and magnetism. So one example is this: you can in gallium arsenide you can actually use this photoluminescence to access this fractional quantum Hall states. Okay, so you by looking at the sample with a laser, you can actually extract the information where the gap state actually form. Another thing that we can examine is by so-called circular dichroism measurement that directly probe the magnetism. So what you see is the monolayer magnetic semiconductor chromium trion that when you swing magnetic field up and down, you can see this hysteresis loop, basically hallmark of ferromagnetism, because you need certain energy to actually feed the spin of the whole layer. Okay, another hallmark of the ferromagnetism is at the zero magnetic field. Okay, you have revenant RMCD. Okay, you have non-zero RMCD at zero magnetic field. If it's non-magnetic, you basically see zero RMCD. We have this optical local probe, but is this system is like sensitive? If our probe is sensitive to the physics going on inside the system. So to verify this, we want to know if the photo emission of the material is really strong or not. Okay, so the safe way is we just image the band structure roughly, and we know if it's direct band gap or indirect band gap. Basically, if it's direct band gap, this KK transition dominates, and you can get very bright signal from the material. That's what we do. We fabricate twisted bilayer sample and do those nano RPath study on this. And what we can clearly see is that the gamma point is still far away from the K point. Actually, we do extra RPath data to access the conduction band, and now we can see it's actually a direct band gap semiconductor. So it will give us very strong optical signature. So now we have probe, we have system, we now can start to probe this kind of physics. So what the requirement for fractional quantum Hall states is actually fractional correlated states, magnetism, and topological invariant. And our strategy is to probe those states is first using those photoluminescence or photo emission to actually see those correlated states. Okay, where it is, and if it's correlated to a fractional filling. Then we use circular dichroism, basically a sensitive probe to magnetism to see this magnetism. And then we use field-dependent photoluminescence to actually see the dispersion of the states and to see topology. Okay, that leads to the discovery of fractional quantum Hall states. So what we first see is to take this photoluminescence spectrum. We can actually now see that at a fraction, the x-axis is energy, is photon energy. The y-axis is actually the doping level or the filling number of the lattice. So when you fulfill the sample, it's actually fill one of the four bands because it's a K-Berlin model. You have two spin spaces, spin valley spaces, and two orbital. So it's there are four bands. So this fill like the top two conduction band, one of the top two conduction band. So that gives you a gap states. Okay, that's why we're on Euro because you half fill the top two conduction band and you got the gap states. And you also have these fractional states that witnessed by the small kink on the PL. So actually now, if you integrate this PL signal, you can now see two deep, okay, on the spectrum, and the two deep actually correspond to integer state and fractional states. So now we establish that inside the system we have some correlated states going on there, non-trivial interaction induce the correlated states. So now we want to explain why this photoluminescence, this photon emission, is sensitive to the gap states. Okay, so the largest gap state is actually intrinsic gap. It's a semiconductor moire system. So at zero doping, you actually have this neutron exciton that gives you this photo emission at a way higher energy. Okay, that's the neutron exciton. When you use laser to scatter a hole to the electron, they bond together and give you photoluminescence. Okay, so now you dope it. The exciton emission you got quenched to become trion. Okay, and then if you form a gap again at this fractional filling, you actually get this quenched of this hole sitting on the Fermi sea, and then you quench the trion population and you got less emission. So that's why you see the photoluminescence got quenched. And this is a good sense of the gap. Okay, the second thing we want to check is magnetism. So very simple, we sweep out our two gates of the sample, and now we can map out the phase diagram of the doping and the electric field. At the zero electric field, we can see a large continuum of correlated states of magnetism, especially on these correlated states, nu equals to -1 and nu equals to 2/3. Okay, by sweeping the magnetic field back and forth, we see this hallmark hysteresis, basically ferromagnetism on these correlated states. Okay, so now we are confident to say that we also see magnetism inside system. The next thing is to verify the topology. So the strategy is very simple. We take that photo emission spectrum again. X-axis is energy, Y-axis is doping. But now we are changing magnetic field and retaking this data again and again. Okay. So now what I can do is that I can eyeball it. It's not start to shift, right? So it has some topology there. That's good. But we need a detailed data analysis to actually extract the slope. So what we do is that we can integrate those spectrum to be a single line and stack them together to form this so-called optically detected Landau fan diagram. And those fan-like structure is actually the slope of it is actually the chain number, as we learned from Stratus Formula. So by extracting the slope, we can now say, oh, it has a shifting, right? But and it's quantized the shift. So we are pretty confident you also see a topology of it. But people may ask, oh, what if you just have a shift of your beam spot, etc., because it's a local problem? So what we can do is that we can go to the electron side, basically the conduction, the total conduction band of the MoTe system, and there's no magnetism at all. And we can see that all those fractional states, they are also fractional states. They are basically charge density wave or generalized Wigner crystal inside the system. And by magnetic field, actually the gap doesn't shift at all. Okay, so we are confident that we are not doing something stupid. So it's a control experiment to our work. So now we discovered this fractional quantum Hall states. So how about we see it in transport? What's the observation of this fractional quantum Hall effect? So actually, we have our one last probe is our transport measurement. Normal probe only is local, but this one is special. It's non-local. It's actually global. Okay. So the experimental challenging actually is to solve the contact problem and also improve the sample homogeneity. So that's what we do. We actually develop in the past year, we actually developed a lot of technique to actually make the sample more homogeneous. And by optical probe, we can verify that the whole sample is magnetized at a zero magnetic field. Okay, so if you take a resistivity map as a function of doping and also electric field, you can now see that the several resistance dip happen in the phase diagram. Basically, your longitudinal resistance at the phase diagram goes to almost zero at nucleus minus 1, and has those pockets at the nucleus 2/3, and very astonishingly at 1/2. The whole resistivity also got quantized even at a very small zero magnetic field. Okay, if we would take a closer look at the phase diagram, we can check the strata slope from transport measurement. Basically, we measure Rxy as a function of magnetic field and doping level. And we also see this strata shift. Okay, so parking at the nucleus minus 1, we can do this quantum anomalous Hall sweep. We see this hallmark of topological states. Basically, you have quantized Rxy and zero Rxx, and it can changing with electric field. Okay, so we can let me go through the data rather quickly because it's the time is up. So at the nucleus minus 1 state, we see this quantum anomalous Hall states. We have quantized Hall conductance, and we measure some important parameter that you are interested. The critical temperature is 14, but the charge gap is as large as almost 28 Kelvin, and we see gapless states at the critical electric field. Okay, at the fractional state, we also see quantized Hall conductivity and with very small Rxx. Okay, and by checking temperature dependence, we can see that the fractional states, the fractional quantum anomalous Hall states actually sustain to 2 Kelvin. Okay, that's way better than a normal fractional quantum Hall with respect to large magnetic field, and it's also electric field tunable. We extract the gap is around 21 Kelvin, and the other state, the 3/5 states, is actually has a slightly smaller gap that is around 80 Kelvin. And the extra thing we observe is actually a very unexpected state that has quantized Hall conductance at 2 HLV square and 1/2 states. Okay, and this can be reproduced in a second device. Okay, but the Rxx is not actually going to zero in both devices. It has a residue Rxx about 2 kilo ohm for this device and around 10 kilo ohm for the other device. Okay, so we can take a line cuts at this zero electric field, and we can see there are indeed plateau associated with 2/3 state and 3/5 states. Okay, but there's no plateau associated actually with this 1/2 state. Okay, so that reminds us in our optical data, actually there's no gapped feature actually happen at this half filling. Okay, so the takeaway is that at the one half state, there's an absence of plateau. There's no plateau. It's very suspiciously gapless state. Okay, there's no absence of PL detected gap. There's no gapped feature here. And the candidate states, actually, we rule out this gapped fractional quantum Anomalous Hall state because in our temperature, the RxX is never 0. Okay, so let me let me unsafely say that it's probably not a gap state. It's a gapless state. Okay, so now let me conclude. Actually, with this transport measurement, we actually conclude that we discovered this fractional quantum Anomalous Hall effect that previously observed in our optical measurement. And that's the talk today. Yeah. Let me summarize with this phase diagram. We actually observed this fractional quantum Anomalous Hall state together with the integer quantum Anomalous Hall states. And actually, there are lots of things going on with the phase diagram. And maybe you can refer to this correlated magnetic states inside the system. Okay, thanks.
Thank you very much for this rather amazing talk. And your timing is pretty good because we started a few minutes late. So we roughly have a bit over 4 minutes left for questions. So if people have questions, feel free to unmute yourself. Speak up.
I ask. Yeah, so thanks for the talk. This work is absolutely wonderful. So for this nu equals half state, your RxY is very, very close to 2H over E squared, right? As you say, your X is not quite 0, it's 2 kilo ohms or something. Now, if I were to contemplate a gap state at nu equals half, it probably has a smaller gap than at, say, nu equals 2/3 or something. So you said it's not gap. So can you put a bound on the gap from your experiment?
You mean for the one half state, the bound of the gap? It's actually pretty hard for us to extract it because if you look at the measurement, these states, you see the resistance, the RxX. Basically, we extract the gap from RxX. It goes up, that goes down. So we don't have a formula to actually fit this curve to give you the gap, right? So we don't actually, if it's gap or gapless, because the RxX never goes to 0. So we cannot safely use that formula to bound the gap or gapless of it. But as our temperature goes down, we didn't see this drop. So 100 millikelvin, that's a good estimation. It's not gap, still gapped at 100 millikelvin. That's what I can give you. Yeah.
Yeah. And the optical measurement, what's the resolution?
The optical resolution, actually, we take optical resolution, optical measurement actually at 2 Kelvin, 1.6 Kelvin, exact. That's the exact number. So at 1.6 Kelvin, all these states is very clear gap in these three states. Okay, so the gap of the charge gap of this the new experiment one state is 30 something, and these two states are 21 and 18 Kelvin. So they are at the order of 20 Kelvin. So these should be less than like 5 Kelvin. That's what I can estimate. Because if it's a 5 Kelvin charge gap, I can definitely see it in my photo emission measurement. So from optical measurement, it's less than 5. Yes, at least.
Yeah. Thank you.
Thanks, Senthil. Are there any other questions?
If no one has a question, I could ask one more.
Go ahead.
So have you looked at the sensitivity to current in the quantized Hall measurement? Can you change the field with the current?
We can change the magnetization with current. That's I can definitely tell you. Yeah.
So can you change the coercive field? Can you move it around?
Yes, the coercive field is actually very sensitive to excitation curve. So if you use say 3 nanoamp or something, the coercive field actually goes down a lot. With 10 nanoamp, basically you see no coercive field. But with in all of the transport measurement is actually 0.5 nanoamp. It's 500 picoamp. It's very small current excitation. With larger at a large current, the first thing you see is that the quantization got worse. The second thing you see is the decrease of the coercive field. And with a very large current, and at this gap, those metallic states, you can flip the magnetization. Yeah, that's a very recent progress of ours. Yes, we can see it in optics and also see in transport.
So that's very similar to the anomalous Hall effect in graphene.
Yeah.
Great. All right, so then if anyone has more questions, feel free to stick around. It'll be kind of a free discussion period after the next talk. So Jiaqi, let me thank you again for a great talk. And then Yin-Shen is up next from Perimeter Institute. And I'll stop the first recording.